So what are we actually made of? I mean, it's the ultimate question, isn't it?
It absolutely is. Forget earth, air, fire, water.
Yeah, the old philosophical ideas. Modern particle physics gives us something, well, much stranger and definitely more complex.
That's the standard model. It's our best map, but it's stunningly complex. And like you said, still really incomplete.
Right. And that's our mission for this deep dive. We're digging into the core source material, basically giving you the shortcut to understanding the essentials.
We're pulling from an advanced physics text, focusing on the core ideas matter, forces, how we try to unify them.
And yeah, this stuff is dense, super dense. But we've tried to pull out the key things, the surprising bits.
The things that define what we know, but maybe more importantly, what we don't know. The big gaps.
Okay, let's dive in. And maybe start with power, the fundamental forces.
Good place to start. Because they are wildly unequal.
Wildly. Like if we set the strong force, the one holding nuclei together, if we set that at 1,
Then the electromagnetic force, which governs light and chemistry, is already way down, about 10 to the minus 2.
tiny. And the weak force, the one behind some radioactivity.
Even smaller, 10 to the minus 7. Barely registers on that scale.
And then there's the big one, cosmically speaking, gravity.
Ah, gravity holds galaxies together, but here, in particle physics,
It's nothing. What's the number again? 10 to the minus.
10 to the minus 40. It's astonishingly weak at this level.
40 zeros after the decimal point.
Yeah.
It's fundamentally negligible for what we're talking about today.
Exactly. We basically ignore it when we're looking inside a proton. The micro and macro worlds are just governed so differently.
Okay, so let's do the inventory. What is this stuff?
Well, broadly speaking, matter falls into two main classes, leptons and hadrons.
Hadrons being things like protons, neutrons, the composite stuff.
Right, made of quarks. But let's start with leptons. Simpler in a way.
Okay, leptons. That's the electron, right?
Yeah.
And its heavier cousins.
Precisely. The electron, the muon, and the tau, plus their partners, the 3 neutrinos. 6 leptons in total across 3 generations.
And the sources really stress the electron's stability. It's incredible.
Oh, it's mind-boggling. The experimental limits on its lifetime are, well, the number is $4.6 times 10 years. Longer than the age of the universe by many, many orders of magnitude.
So for all practical purposes, forever.
Pretty much. Meanwhile, the neutrinos are the opposite end of the spectrum, almost massless. We know they have mass, but it's tiny. The electron neutrino, for instance, is less than 2 electron volts.
Almost nothing.
Okay.
So those are the leptons. Now the quarks, the building blocks of, well, us.
Right. Quarks make up the hadrons. Like leptons, there are 6 of them, 6 flavors. Up, down, charm, strange, top, and bottom.
And they have those weird fractional charges.
Yep. Plus 2/3 or minus 1/3 of the electron's charge. And the amazing thing is pretty much everything you see, everyday matter, is just the first generation.
Just up and down quarks. A proton is 2 ups and a down. A neutron is 1 up and 2 downs.
That's it. The visible universe built from just those 2.
But the mass difference between these quarks, that's where it gets wild again, isn't it?
Absolutely dramatic.
Yeah.
And it's a huge puzzle. The up and down quarks, or their constituent masses within hadrons, are maybe around 0.3, 0.5 GeV. Pretty light.
Okay.
But then you jump to the 3rd generation, the top quark. It weighs in at around 172 GeV.
Whoa. 172 GeV. Compared to less than half a GeV, that's hundreds of times heavier.
Exactly. Within the same family of particles. It's like having a house cat and a blue whale in the same category with no explanation for the size difference.
It just screams that we're missing something fundamental about mass. Okay, so that's the matter inventory. What about the forces again? We mentioned the weak one.
Right, the weak force. It governs processes like beta decay when a neutron turns into a proton.
Emitting an electron and an antineutrino.
Correct. And the key thing our sources highlight is its range. It's incredibly short range, only effective over distances like 10 to the minus 16 centimeters.
Which is tiny, even for particle physics.
Extremely tiny. And that short range is linked to its energy scale, which is actually quite high, around 300 GeV, because the particles that carry it are massive.
Okay, and then the strong force, the one holding quarks together inside protons and neutrons, that's QCV, right?
Quantum chromodynamics, yes. And this one's mediated by gluons. It's based on a different kind of charge, not electric charge, but color charge.
Red, yellow, blue. Though it's just labels, not actual colors.
Right, just names for 3 types of charge. Quarks carry color, and crucially, the gluons that mediate the force also carry color charge. That's different from electromagnetism, where the photon is neutral.
And this leads to some really weird properties.
2 very striking properties, almost contradictory, actually. First, asymptotic freedom. Meaning, if you probe quarks at very high energies, or equivalently, very short distances, the strong force between them becomes weak.
They act almost like free particles when they're really close together.
Pretty much. Bouncing around inside the proton or neutron relatively freely.
Okay, that's weird. But then the other property
Is confinement. Try to pull those quarks apart.
and the force gets stronger.
Yes. The potential energy holding them together grows linearly with distance. VRs is proportional to dollar.
Linearly.
Yeah.
Not falling off like gravity or electromagnetism.
Yeah.
So the further you pull, the harder it pulls back.
Infinitely harder, in theory. The energy required to separate a single quark to infinity would be infinite.
Which means you can't. You can never actually isolate a single quark.
Exactly. That's why we only ever observe colorless combinations, hadrons like protons, 3 quarks with canceling colors, or mesons, quark-antiquark pairs.
Yeah.
Nature enforces this color neutrality.
Wow. Okay, that linear potential,
Yeah.
that's a fundamental constraint on reality.
Yeah.
So this whole picture, quarks, leptons, forces, this is basically the standard model.
This is the heart of it. The modern view rests on those 3 pillars we've touched on: the quark hypothesis, electroweak theory, and QCD.
And a huge achievement was unifying 2 of those forces, right?
Yeah.
Electromagnetism and the weak force.
Absolutely. Electroweak unification. At everyday energies, they look totally different. One's long range and relatively strong, the other's short range and weak.
But the theory showed
That at very high energies, around 250 GeV, they merge. They become different aspects of a single underlying electroweak force.
that's a massive energy scale.
It is, and making that unification work required figuring out why the force carriers are so different. Why is the photon massless, giving electromagnetism infinite range?
While the weak force carriers, the W and Z bosons, are really heavy, which
Wow.
explains the short range.
Exactly. And the answer, or at least our current answer, is the Higgs mechanism.
Ah, the famous Higgs, spontaneous symmetry break.
That's the one. The idea is that the underlying equations have a certain symmetry, but the universe's ground state, its vacuum, doesn't respect that symmetry,
And this breaking gives mass to the W and Z bosons.
while leaving the photon massless. And the energy scale associated with this symmetry breaking, this Higgs field, is right around that electroweak scale. Val dollar approx $250 GeV. It all ties together.
It's elegant and incredibly successful experimentally.
Phenomenally successful. But, and this is a big, but the sources constantly emphasize, it's incomplete. Profoundly so.
Right. For all its successes, it leaves so much unexplained. If you had to pick, what's the most glaring hole? The thing that keeps physicists up at night?
Oh, there are a few big ones. One major mystery is just family replication. Why 3 generations?
Yeah. Why the muon and the tau? Why the charm, strange top-bottom quarks? They seem like heavier copies of the first generation.
Exactly. The standard model just puts them in by hand. It offers 0 explanation for why there are 3, not 1, not 5. QCD, for example, doesn't care how many quark flavors there are.
It feels arbitrary, like finding spare parts you don't know the purpose of.
Kind of. Then there's the origin of fermion masses,
Yeah.
even with the Higgs mechanism.
It doesn't predict the actual mass values.
No. The Higgs gives particles mass through their interaction, or coupling, with the Higgs field. But the strength of that coupling for each particle, why the electron has its mass, why the top quark is so heavy, those are just free parameters. We have to measure them and plug them in. There's no theory predicting them.
So 20-something parameters we just have to measure, with no deeper reason why they have the values they do.
That's the situation. We're also still hunting for a rigorous mathematical proof of quark confinement from QCD first principles.
That linear potential thing,
Mhm.
proving it mathematically is still an open problem.
A major one. And then there's the origin of CP violation.
Okay, CP violation.
Yeah.
That sounds technical, but it's crucial, right?
Hugely important. Symmetries are fundamental in physics. So Noether's theorem tells us that symmetries lead to conservation laws. Like symmetry in time leads to energy conservation.
Got it. So C is charge conjugation, swapping particles and antiparticles. P is parity, like looking in a mirror.
Right. And strong and electromagnetic interactions seem to respect C and P individually. The weak force, however, violates both C and P quite dramatically.
Treats left and right-handed particles differently, for instance.
Exactly. But for a while, it was thought that the combination, CP, might still be a good symmetry. Swap particle for antiparticle and mirror reverse. Maybe that stays the same.
But it doesn't.
It doesn't. Experiments, particularly with particles called kaons, showed tiny violation of even CP symmetry in weak interactions. There's a measurable parameter, often called epsilon, which is small but definitely not zero.
And this tiny crack in the symmetry,
Yeah.
this is somehow essential for, well, for existence.
It's one of the necessary ingredients, yes. For explaining baryogenesis, why the universe is full of matter and not antimatter. You need CP violation for that. We exist because of this subtle imperfection.
Okay, so standard model, great, but incomplete. What's the next step? Where do we look beyond it?
The dream for decades has been grand unification, or GUT's grand unified theories.
Taking that electroweak unification one step further.
Exactly. Trying to unify the strong force, governed by its symmetry group, SU3 of color, with the electroweak force, which is SUL2, XUY1, combining all three non-gravitational forces into one single framework.
That sounds ambitious. How would that even work? The forces seem so different.
The key theoretical tool is the idea of running couplings.
Ah, you mentioned this earlier. The strength of a force isn't actually constant.
Correct. The coupling constants, like alpha for electromagnetism or alphas for the strong force, actually change their value depending on the energy scale you're probing.
So they run with energy.
They run, and the core idea of GUTs is that if you run them up to extremely high energies, maybe they all meet.
All three lines, strong, weak, electromagnetic, converge at some incredibly high energy point.
Precisely. A single point, the GUT scale, often labeled mx dollars. At energies above that, there would just be one unified force described by a larger symmetry group. Below that energy, the symmetry breaks and the forces split apart into the three we see.
That's a beautiful idea. Does it look like they meet?
Well, the original, simplest models predicted they'd meet. But the experimental data we have, particularly from precision measurements, shows they almost meet, but not quite.
Close, but no cigar.
Sort of. Introducing other ideas, like supersymmetry, can help make them meet more nicely, but that's another layer of complexity and hasn't been experimentally confirmed yet. So GUTs remain a compelling theoretical goal, but not yet proven reality.
And these incredibly high energies, they connect particle physics directly to cosmology, right?
Huh.
To the very early universe.
Absolutely. You can't understand the first fractions of a second after the Big Bang without particle physics. The physics driving the universe then was high-energy particle physics.
Like the idea of inflation.
Inflation is a great example. This period of incredibly rapid, accelerating expansion in the earliest moments. The conditions required for that, like a specific parameter epsilon being less than 1, depend directly on the properties of particle fields at those energies. Particle physics dictates cosmology.
And cosmology throws up maybe the biggest question for particle physics to answer. Why are we here? Why matter?
Baryogenesis, yes. The universe we see is overwhelmingly matter. Protons, neutrons, electrons, there's virtually no primordial antimatter left.
But the Big Bang should have created equal amounts, right? Matter and antimatter.
According to our basic understanding, yes. For every particle and antiparticle, they should have annihilated each other, leaving just energy.
But they didn't. There was a tiny imbalance. Something like 1 extra matter particle for every 10 billion pairs.
That's the scale of the asymmetry, delta B approx 1010. Tiny, but it made all the difference. That slight excess of matter is what formed all the stars, galaxies, and us.
And explaining that excess requires some specific conditions from particle physics. We mentioned CP violation.
Yes, that's one of the three Sakharov conditions. You need CT violation, you need interactions that violate baryon number conservation, meaning you can actually change the net number of baryons.
So protons can, in some way, be created or destroyed or interconverted.
Under the right conditions, yes. And the third condition is departure from thermal equilibrium. You need things to be dynamic, not just settled.
And these conditions, they likely existed only in the extreme heat of the early universe.
That's the idea. Particularly the baryon number violation. At low temperatures like today, proton decay, if it happens at all, is incredibly rare. But at very high temperatures,
Things change.
yes, there are theoretical mechanisms, non-perturbative effects, sometimes called sphalerons, which become active at high temperatures. These are like pathways that allow baryon number to change. Thermal fluctuations essentially open temporary doors that are normally locked shut at low energy.
So the heat of the early universe provided the environment for these subtle rule breakings to create the matter imbalance we see today.
That's the leading picture. It connects the deepest laws of particle interactions to the largest scale structure of the cosmos.
Okay, so let's recap this whirlwind tour. We started with the basic inventory. Quarks and leptons, the building blocks,
6 of each in 3 generations with wildly varying masses.
governed by 4 forces, 3 of which, strong, weak, electromagnetic, are described incredibly well by the standard model.
which itself relies on QCD for strong force and the electroweak theory, unified via the Higgs mechanism for the other two.
A stunning achievement, but one that leaves huge questions unanswered. Why 3 generations? Where do the masses really come from? Why the specific symmetries and why the specific violations like CP violation?
Exactly. The standard model works phenomenally well in its domain, but it feels incomplete. Like a very detailed chapter, but not the whole book.
The search for the next chapter involves things like grand unified theories, trying to merge all the forces.
Relying on complex but beautiful ideas like running coupling constants, hoping they point to a single origin and immense energies.
And ultimately, these particle physics laws aren't just abstract equations. They have to explain the universe we live in.
Which brings us back to that profound asymmetry, the matter dominance.
So, here's the thought to leave you with. The rules governing the smallest things we know must also explain one of the biggest cosmological facts, why everything is made of matter. What deeper principle, what currently hidden symmetry or mechanism, dictated that tiny imbalance billions of years ago, ensuring a universe filled with stuff rather than just light?
Finding that connection, that's the quest. That's where the next real revolution in fundamental physics likely waits.